Subsystems in the satellite also. So each has 5 subsystems. When we consider the total satellite, we divide it into 5 subsystems. One is called TTNC, telemetry, telecommand, and command. TTNC. First is telemetry, second is tracking, third is command. Telemetry, tracking, and command subsystem is one subsystem which is needed in order to keep the satellite there, track it and control it. But it is not communication part, it is mainly for keeping the satellite. And therefore there is another one, similar one called AOCO, which is called attitude control subsystem. And third one is the communication subsystem. And our earlier diagram, the power planning and everything, big power budget and everything is for the communication subsystem. It is only one of the 5. Fourth one is the antenna subsystem. Fifth one is the electrical and the bus, we call it bus subsystem. So therefore altogether it's the assembly of 5 subsystems. Communication and antenna subsystem are needed for our calculation. Other things are for keeping the satellite there. Okay? So you can write subsystems of a satellite. Subsystems of a satellite. Number 1, AOCA. Which is attitude and orbit control subsystem. A for attitude and O for orbit control. Attitude and orbit control subsystem. Number 2, TTNC. TEN. T stands for telemetry. Second is for tracking and command. Telemetry, tracking and command subsystem. TTNC subsystem. Third one, power subsystem. This is for electrical mainly. Power subsystem. Number 4, communication subsystem. Number 5, spacecraft antennas, and antenna platform subsystem. Spacecraft antennas and antenna platform subsystem. So those are the 5 things we have to put together to make the satellite. What is the rate of the satellite normally? weight is above 1 metric ton for communication satellite. Okay? This means when you put these 5 subsystems together, for a communication satellite, the weight is above 1 metric ton, above 1000 kilograms. And therefore they are called macro satellites. Macro satellites. Macro, large satellites. But today satellites have gone some these are the names for the satellites today: nanosat, picosat, microsat and macrosat. Macrosat is mainly for communication. And microsatellites are less than 500 kilograms. Somewhere between 100 kilograms and 500 kilograms. Mainly for mapping applications, mapping, disaster management and that kind. And picosatellites are around 10 to 50 kilograms. And nanosats are 1 to 10. Now you can see satellites are very wide range, and our syllabus has only this. And Sri Lanka is going to have a microsatellite soon by next year. Government has decided for it. In fact, they decided it yesterday. And there was some news item some time back, about a month ago, about pending decision. And yesterday they didn't still announce that it is finalized. We are not going to, we are owning. We are owning lot of, for example, motor vehicles which, now our people own motor vehicles but they are not Sri Lankan. For example, that one might come from India. Likewise, satellite may be not immediately made here. Initially it will be owned, but over 3 years the capacity will be slowly transformed here to make not big ones but microsats. Microsats are small, and a microsatellite is just like one person, weight-wise, and size-wise it is something you can lift. So the difficulty in manufacturing is you need clean rooms. At least 3 clean rooms, one after the other, is required to manufacture. Other than that, it's not a big system. But microsatellite is like a motor vehicle. It's a big one. Picosatellites are things like this. Small. So picosats are normally university students manufacture them normally, and in other countries most picosats are manufactured by universities and as student projects. And after the design is done, then they take into the clean room and do it cleanly so that it can be sent to the state. So that's why Morato is also involved in this because our university students will have to do part of it. And some other part will be done there initially until we get the clean room. So likewise, what I am trying to say is that you might have thought satellite manufacturing is a big one, $billions, but it is changed. It was. But still this part is far away, even for Sri Lanka to own a micro, not to manufacture, but just to own it will take about 5 years from now. It is highly priced. But these things are for experimentation. These are not for communication. It is to experiment various things like new cameras and then earth mapping and so many things. Like you would have seen satellite pictures of people moving in the certain areas. You have seen that on TV. So these are the satellites which go there, not those. So initial satellites will be somewhere here, somewhere around 100 kilos. The initial satellite. And now the launching of satellite is the costly part, not manufacturing. For launching you have to hire companies, and that is where the money goes. Okay. So just be aware, mention this, be aware that satellite technology is completely changing. And most of the picosats and nanosats are on very low Earth orbit, less than 1000 kilometer orbit, not 36,000 kilometer like the geostation. And nanosatellite programs are coming for various other applications like even cellular. Base stations might go into nanosats in future, we don't know. People predict. Then you don't need to construct towers in there. But some of you might lose the job. Right? Anyway, it is not very close. Right? I am just predicting what could happen if these projects go on. And initially also when satellite communication was proposed, people didn't think that it will take this much of progress, isn't it? But today a lot of people watch satellite television, so many people use the satellite today. GPS, many people use, and slowly GPS is coming to the mobile phones also, all satellite based. So similarly, these new programs like picosat, nanosat programs might have big effect in the future, because they are not very high cost. That is the main advantage, and they are not going at very high altitudes also. Therefore, power levels you can get on Earth are good. And more than that, today it is mainly also imaging. You can image any part of Earth using cameras. And the camera resolutions, the CCD resolutions are becoming better and better over the years. So very small, high resolution cameras are coming. And with that, these satellites will have a lot of applications. Not for communication, but for a lot of other things. Okay. Therefore, satellite applications are changing from communication to some other area now. If you look at carefully. Okay. But your syllabus has only communication. I just put this for your knowledge. Right? Communication is not the only thing. Forget it. Okay. Then you can say. But remember that even if it is 10 kilogram nanosat, the 5 subsystems period must be there. 5 subsystems must be there. That means you will have to make it smaller and smaller. Subsystems are general. They have to be there, otherwise satellite will not run. You can mention in the full range of these satellites, each should have all 5. Each should have all 5 subsystems. Each should have all 5 subsystems. One good example is now, sometime back there was Katrina, some disaster which came to US, remember? They wanted to analyze satellite pictures of that area, the affected area, to find the details, where people are, how to rescue them and all that. And US found that the best pictures came from Nigeria side. Nigerian satellite which is doing imaging. Right. And that means, because US was mainly concentrating on communication satellites and entertainment like TV. The imaging sets, they had a big program called Landsat. I'm sure you have seen the Landsat pictures, which was a superior system long time. But Landsat satellites are now having poor resolution compared to today's camera. So therefore Landsat is coming to the end of its lifetime. Pictures are not high resolution. But this Nigeria sat was a recent one, and that gave the best pictures of Katrina. So those are examples of how the technology has changed. And I'm not sure whether you knew Nigeria has satellites. A lot of poor countries have satellites today because they can afford these small satellites. Right? Mainly countries having large area which they can't monitor easily, they go for these satellites because the satellite goes over it many times and you can monitor the country. Sri Lanka might not need to be monitored like that, I don't know, because it's a small country. But large countries, they need satellites. even to monitor their props. When you look at from the top, the picture of the paddy field shows certain area little brown, certain area green. Then you know where to fertilize. Otherwise, large regions like that you can't walk and find. But in a small country like this, you can always find by walking. But larger countries have different problems. So for them, these applications are very powerful for them. Okay. We'll take them one by one. You can write first one, KOCS. KOCS. Attitude and orbit control. You take a satellite, the geostation is orbit. So, GEO means geostationary orbit. Circular orbit. Suppose there is a satellite here. Position of the satellite is equal to radius of the geo, longitude and latitude of this subsatellite point. It is the Earth center. It is P dash. P is the position. P dash is the subsatellite point. Subsatellite point is on the equator. This line you see. R theta phi. This axis you call yaw axis. Axis joining satellite position to the Earth center is called the yaw axis. Then vertical axis to this point is called pitch axis. Then tangent to the satellite orbit, which is also making 90 degrees with this. You understand what I'm saying? It's called roll axis. Controls here, you need controls in order to keep the satellite there. One is known as orbit. That means maintaining the orbit. Two is position control. Position control on the orbit. Three is attitude. Those three controls are needed to keep the satellite at the required position and not allowing them to roll around any of these three axes. Orbit control you can easily understand. This orbit should be of the same shape and radius all the time. It should not be tilting up or down, or it should be making elliptical. Shape and the orientation must be maintained. That's called orbit. Position control means within the orbit which place. Attitude control means even if it is in this place, it can roll. For example, suppose this pen is right here in this place, but it may be rolling right. It may be tilting this way. For example, if I am sitting here, standing here, my position is fixed, but I can tilt like this. still like that, but my legs are same size. So that is rolling. So attitude control means not allowing it to roll on any of these three axes. It should not roll. That is called attitude. If it rolls, what will happen? The antenna beams will go everywhere. It should not roll because it's pointing the beams to the earth. Even if the position is correct, orbit is correct, attitude is not correct, that means the footprint will go somewhere. So all these three must be controlled. Otherwise, the required service cannot be given to that area of the satellite. Orbit control means maintaining the radius and the orientation. Radius, shape and the orientation of the orbit. Radius, shape and the orientation of the orbit. Next line. Position control means keeping the satellite at the correct longitude and latitude. At the correct longitude and latitude position of the orbit. Longitude and latitude positions of the orbit. So attitude control means, next line, attitude control means not allowing the satellite to roll, over any of the three axes shown in the picture. Roll over any of the three axes shown in the figure. The subsystem which ensures these three controls is called AOCS. These three controls is called AOCS, attitude and control subsystem. Attitude or control subsystem. Attitude or orbit control subsystem. AOCS. And there are methods which are beyond our syllabus, like spin stabilization, momentum stabilization, various techniques used to do that. You can mention example techniques. Example techniques are: number one, spin stabilization. Spin stabilization. That means you allow the satellite to spin, and according to that spin it will remain stable. For example, if you spin 1 rupee coin, you know that it can remain vertical, isn't it? So long as it spins. The moment the spin slows down, it will fall. That is called spin stabilization. If you want the 1 rupee to stand like that, you have to spin. The satellite is also spun. Some satellites are spun like that, and those satellites, by shape you can easily see. By shape, these satellites are like terrain. So they are made for spin. The antennas are mounted on a separate platform like this for the antenna, and this part is sun this way, the antenna one is sun the other way. Typically about 70 revolutions per minute. If you see a satellite round like this, like a cylinder, this means it is spin style. It is rotating in order to maintain its attitude. Otherwise it will roll. Otherwise it will roll over one of these three axes. Okay, then you can draw an example. Like spin stabilized means it's a cylinder, cylindrical shape. I'm sure you know that you also have that kind of a system, attitude control system. Not the normal attitude, I mean. Attitude means the way you stand. Otherwise you can't stand up and walk. So there is a system which keeps detecting your orientation and correct it. Where is it? It's in the it's called mid-ear area. Using a liquid is sand. So without that we will be in trouble. We will not know whether we are tilted. So similarly a satellite has the same need. If it is tilting, it should know and correct. Just like we do. Suppose you are standing and suddenly you are doing like this, you will immediately sense and correct. How do you sense? Using the liquid in the mid-ear, and it gives a signal to the brain. Okay, the liquid is going to one side. So one system is that liquid method, but it is not possible in the satellite. Why? Liquid needs gravitation. There is no gravitation there, so you can't use the liquid method. That's why the spin method is. You can also use the spin method for yourself. Then you can keep spinning, right? But then you can't do anything else. So therefore, the designer, whoever designed this body, thought, okay, liquid may be better. Right? So likewise, stabilization methods are different. Right? One method is liquid, other method is spin. Other method is spin method. There is a third method called flywheel method. Okay? Flywheel technique, which is the gyroscope method. Another example, spinning flywheel method. So those satellites are not cylinders, they are not rotating from outside. Inside those satellites, some flywheels are rotating. So they might have a cubic shape like this satellite, cubic shape. Then wings will be there, antennas will be there. Nothing rotating from outside. And that kind of satellites are internally stabilized, not from external. From outside you can see the spinning what you call flywheel, which is running inside. Okay, so these are all belonging to AOC, attitude and orbit control subsystem. So a lot of techniques there which we are not studying. I am just introducing why it should be there. Then number two, TT&C subsystem. Then you can mention tracking for the data. Tracking means following the satellite. Tracking for the data. Following the path of the satellite. Following the path of the satellite. Telemetry means remote sensing. Telemetry means remote sensing. Command means, next line, command. Put it as giving remote command to the satellite. So Therefore, the tracking system keeps sensing the errors in the position where the satellite should be and where is it now. The error is always sensed by using tracking subsystem. Can write the tracking subsystem continuously calculate. Tracking subsystem continuously calculates the error in the satellite position. The error in the satellite position in the orbit. So the telemetric system has many sensors which keep collecting the status and send them to the Earth station, send them to the control Earth station, send them to the control Earth station. So the command system analyze this information generate command needed to control the satellite. And send them to the satellite. We try to draw it as a figure. We have the satellite. And there will be a special antenna like this, which is communicating with two receivers from this. This is not communication. Communication is coming and going like this. This is control, right? Not communication. This is one is called elementary receiver. Other one is called tracking receiver. Both the outputs go into AOC. AOC is like controller. They separate things like this. It is called any command list. Two different frequencies are used for this. Your communication goes via the antenna. This antenna, so antenna system is used for this term, AOCS term. So these are the costly parts of the satellite. Not mainly communication part, but doing all this online continuously without errors is very difficult. You need a lot of accuracy. Otherwise, if the satellite goes out of your control, you can't get anything from that. After that, it is lost. If it goes out of this loop, that satellite becomes useless. No one can control. So it is a loop like this. It is just like how your brain controls your body. Your body has many sensors. The brain keeps tracking of what is happening and then generates commands to your muscles. The same idea. And the moment that loop is open, you know that your body is useless. You can't control it. So same thing. Okay. If the loop is broken, the body cannot be controlled. Same way, satellite cannot be controlled. After that, it becomes useless. Actually, it goes away from its position and you can't correct. Show this continuously running loop. It is called a closed loop control system. So AOCS is a closed loop control system. Then third one, communication subsystem. Communication subsystem. Repeater block diagram. Of RF heterodyne repeater and baseband heterodyne repeater. RF heterodyne repeater and baseband heterodyne repeater. Now that is the block diagram of the communication subsystem. We already drew it, but what we have drawn is only one channel. One channel like that is called a transponder. And there are many transponders like that on the satellite. Sometimes 10, sometimes 50 transponders. All together, all of them are called communication subsystems. Can write. One such repeater is called the transponder. It has the bandwidth of 36 or 72 megahertz. There are many transponders. There are many similar transponders. In the communication payload, of the satellite. Communication payload of the satellite. Underline communication payload. Payload means people are ready to pay for the service given by that subsystem, but people are not ready to pay for this. Supposing somebody says, okay, I am tracking my satellite, can you pay me? Nobody will pay. Instead, if there is a communication subsystem and you are using it, you are ready to pay. So that's why it is called payload. This is not payload, this is called the bus load. Bus subsystem means if nobody is ready to pay for that, it is your own problem. It's like some space is needed in a bus to carry the engine, the driver, the conductor. No one is paying for that. Conductor is also traveling, but conductor is not paying the owner. Owner is paying the conductor. So, overheads, isn't it? They are overheads, but necessary. So, communication part is not an overhead because people are ready to pay for the bandwidth. Next one, antenna subsystem. consists of oval antenna on the satellite. Example, some antennas are like this. One is called horn antenna. Example, horn antenna. Another one, dish antenna. Dish antenna. Another one, phased array antenna. Phased, P-H-A-S-E-D. Phased array antenna. Another one, omni antenna. Omni. So likewise, various antennas are there. All that we call antenna subsystems. Okay. So those are the 5 subsystems that are combined to make a satellite. Then in order to launch the satellite to that orbit, you have to hire a launch vehicle. And there are 2 types of launch vehicles. Power, just that power. This type, power subsystem. Power subsystem, and that consists of fuel, solar panel, battery bank, electrical buses, etc. Yeah, everything related to the power. That's called the power subsystem. Right. Regarding launching, then, there are 2 vehicles that can carry satellites to the orbit, and that is the most expensive part in satellite formation. One is called shuttle type. I think you have seen the space shuttle going and coming. Space shuttle is something which can carry a satellite, allow it to pass there and come back. The other type is self-destroying. It's called SST type. Shuttle type is SST. Other one called ELV type. And that type is carrying the satellite and self-destroying. Right? And that means the whole cost of that shuttle you have to pay if it is your satellite. Right? So it's getting destroyed. So you can write satellite launching, launching, and there are 2 categories of launch vehicles. 2 categories of launch vehicles. Number 1, ELV type. ELV, expandable launch vehicle. Expandable launch vehicle type. Expandable launch vehicle is having 3 stages like this. Connected with power booster on the side. These are called booster engines. They are needed to go from get escape from our atmospheric gravitational force. These boosters are for that purpose. This is the main. This area is fuel tank. This area is called oxidized gas. And this is the main engine here. Main engine here, and this whole area is called the 3rd stage. This is called 2nd stage. object is here. Inside this first stage you will find the turbine. Second stage has an engine here. Second engine. And here you have a little engine called first engine. Third engine is the main engine of the ship. This is the design of the EL-beta. Expandable launch vehicle means it expands part by part. It removes this one after it takes you into the outer space. Then goes in with pin here, then finally launch using the third engine. Launching process is a three-stage process. Like this. This is the to identify a low something called parking only, and you can give a view. Parking orbit is within about 1,000 kilometers smaller. So using the booster, using a launching pad, you will launch it onto the parking orbit and it comes like this. So your main engine and this main fuel is wasted for that, overcoming the gravitational force and going. After that it is the second engine which carries somewhere here motor fires and give a velocity like this, and it goes into a elliptical orbit. Over the elliptical orbit you wait until it comes here. After that you fire another motor and get it moving in this way. And this part of the orbit is never used. This is called GTO orbit, geostationary transfer orbit. This one is fast. So three stages. Now first stage is this. Second stage is this. That's why you need three engines. Each part is for each stage. After that is served, you remove that. So slowly the vehicle gets destroyed part by part. Third stage is for this purpose, for stage 1. This is for this purpose. This is for that. Third engine is to give the speed up. This velocity. You fire one motor called Perigee motor here. Another motor. One motor fires here in order to change the orbit. Another motor fires here to change to the other orbit. Actually, they are those engines. The second stage and third stage engines are the two which fire. Okay, parking orbit is a circular one, GTO is a elliptical one, GEO is a circular one. Maybe you should mention, parking orbit is circular, GEO is circular, GTO is elliptical. For sending the satellite to elliptical, you don't need fuel, that is why we use it. This is natural orbit. If we have to spend fuel for this, we need a lot of fuel to go this 36,000 kind of kilometers. And we have to go up to about 1,000 by spending all this fuel. After that, it is automatic because we are using Kepler law. in order to carry the satellite up to the third one. Then we need the other engines in order to give those velocities, only the initial velocity. Otherwise, to carry something 36,000 kilometers, you need a lot of fuel. To go home, I need few liters of petrol. 36,000 kilometers, you can imagine. Therefore, we use autogear, automatic technique, which is the elliptical orbit. Elliptical orbit does not take fuel, it goes automatically. So that is the technique we use. Okay, that's ELV, the most popular method, but the other method is shuttle method, but little more expensive. Number two, SST, space shuttle type. Space shuttle type. And that you can write. This is the reusable. This is the reusable space shuttle. Reusable space shuttle which position the satellite and return. Position the satellite in parking orbit, and return. In the parking orbit and return. So, two techniques, ELV type and SST type. Those are launch vehicles, satellite launch vehicles. But that is the most expensive part of the process. So that I can say, launching is the most expensive part of the development of the communication satellite. Development of a communication satellite. In some papers they ask to write advantages and disadvantages of that orbit also, GEO. So we write that as an answer. You can write subheading advantages of GEO. This is directly an exam paper answer. Right? Advantages of GEO. GEO means geostationary Earth orbit. Number one, always on view. Always on view with the Earth station. Always on view, V-I-E-W, view with the Earth station. Therefore, fixed satellite service, fixed satellite service is possible. In brackets you can write FSS. Fixed satellite service is FSS. Number two, one satellite can cover the maximum surface area of Earth around 42%. Around 42% of total surface area. Around 42% of the total surface area. Number three, minimum of 3 satellites. Minimum of 3 satellites at 120 degrees, 120 degrees angular separation on geo 120 degree angular separation on geo can make the global beam. In the diploma we studied this. Can cover the whole earth. One beam will be 18 degrees. 18 degree 3 beam can cover the whole earth and make one global beam. That is what is proposed by Dr. Clark initially. That's the biggest advantage of GEO. With minimum of satellites, 3, you can get the global cover. If you don't use GEO, you need to more satellites to cover. Fourth advantage, minimum amount of tracking. Minimum amount of tracking is needed. So relative motion is negligible. Minimum amount of tracking is needed. Number 5, Doppler frequency shift is negligible. Doppler frequency shift is negligible. Doppler frequency shift is negligible. Doppler shift occurs when there is relative motion, but relative motion is negligible here, therefore you don't have a frequency shift. Otherwise you have to have a frequency tracker also in your receiver. Right? So those are the 5 advantages. Disadvantages. Number 1, long propagation delay. Long propagation delay is in brackets approximately 250 millisecond round trip. Approximately 250 millisecond round trip. 2, high EIRP required. High EIRP required. 3, high gain antennas required. High gain antennas are needed. 4, poor coverage in polar region. Poor coverage in polar, POLAR, polar region. That means North Pole and South Pole. Polar region. Number 5, very expensive launching. Very expensive launching process. Number 6, heavy propulsion, PROPUL SION. Heavy propulsion devices are needed on board. Heavy propulsion devices are needed on board. So those you can remember as weaknesses of that high elevation orbit. Another question area is normally about how your antenna should be looking at the satellite. Because you have to have your beam at an angle from Earth, isn't it, to see the satellite. And that angle with the Earth is known as elevation angle. If the elevation angle goes below 15 degrees, it is not recommended. You can operate, but service will be so poor. Below 5 degrees, service is even not possible. Poor service is also not possible. Right? So between 15 degrees and 90 degrees you can operate, but closer to 90 is always the best. Why? If you operate at an angle like this, normally when there is a rain cloud or something, you have to penetrate the rain cloud like this. But when you are penetrating, it's very short this way. This way it is very long. Normal rain cloud is about 40 kilometers in length. So it's like you are going through rain 40 kilometers and there will be heavy attenuation in the down. So therefore it's not recommended to have low elevation angles, especially if the satellite is not transmitting high power, because it is heavily attenuated by the rain cloud, and if there is rain, rain will also attenuate in between. And I think some operators have installed this TV, and you know what happens during rain. So because the elevation angle you would have seen is not good. Not good. Maybe going for a cheaper satellite, I don't know. But that elevation angle is a poor elevation. Not 15, but maybe around 20, 30. Big. 45 is fairly okay. But still you can see the rain effect. Maybe mainly because it's KU band. C band is little better with respect to this. So therefore elevation angle matters, otherwise you can't give a reliable service. People will complain. So no, we are talking only about the GEO. If it is pico or micro satellite, it is running on low Earth orbit. Then you have to continuously track the satellite. You can't have the antenna like that. You can have a fixed antenna only for GEO satellite. Otherwise, you have to keep tracking the satellite, and after that track again. After that track again. Like so, for home reception, it is not possible for people to have that kind of tracking. And therefore, it is used for mainly imaging and some research applications, testing applications, and military applications for security. And also, it is used for applications like GPS, where you don't need to track satellite because it's transmitting omnidirectional. But you need high power for omnidirectional transmission. Okay? You can tell. Yes, these are all parked. Geostationary satellites are all in fixed places. Fixed in the sense they are moving with you. You are also moving, they are moving. The relative motion is zero, nearly zero. But other satellites, they are moving fast with respect to it. Then your antenna will have to track them. Each and every has a satellite angle. Because now the Earth is round, depending on where you live. So this is the GEO. Depending on where you live, suppose your satellite you want is here and you are living here, your angle will be like this, not like this. For this kind of satellite, angle will be nearly 90. But for this kind of a satellite, angle will be maybe 45, that's right. But all of them are on the geostationary also. I have seen like they are giving satellite angle around 60 or something using we have to do some calculation part to get the elevation angle. Calculation is normally on the web. If you log on to the satellite operator site, there is a little calculator where you enter your GPS reading, it will give you the calculation part. I done the calculation. They are asking height. We don't have height. Yeah. But height no. But using that calculation, I was trying to grab the analytics. You can't track satellites like that. In order to get locked to the satellite, you need a lot of experience. An inexperienced person will normally spend about 1 hour to get the satellite. Calculator is just giving one thing, but a lot of fine adjustments required between the two actors. Only if you are highly trained, you will be able to do it within 10 minutes. Highly trained. 2 hours means average. Anybody can do it. That within that time anybody can do it. But if you are highly trained with that calculator, 10 minutes will be enough. The calculation is one thing, but practically tracking it, practically aligning it means lot of precision adjustment according to a pattern. You need a lot of training for
I
that.
was found problem. According to my calculation, I thought that from this side, but after the finding that sometimes the reduce is not. It wasn't calculating something wrong. I'm not sure what's going on with this design.
It cannot be. They will not put a wrong calculator on the web.
Calculation means
Maybe something you entered. Maybe.
no, they are giving the like angle and
No, it is your position which will be wrong, because if you took it from a normal GPS, not a very high accurate one, there is about 9 meter, 10 meter error. And if you are calculating from there, there will be a big error in the angle. That is the first problem. It's not the calculator. It's your location.
without that GPS position we can't use the calculator.
You have to verify the GPS by taking multiple readings, so at least high precision GPS.
At the moment I just use the GPS. I use Google Earth position system.
That is nowhere. Google Earth has 3 arc-second error. 3 arc-second means heavier.
Which is that GPS position my without 3 times done.
That cannot be done. Never do that. Right? Google Earth has 3 arc-second error for our map. And if you are ready to spend a lot of money, you can get from Google 1 arc-second map. 1/3 reduced accuracy. 1 arc-second is the best they give out. Other ones are for military use. So with that you can do this professional job. That is why it is taking time. Okay, one exam question is, what are the problems of lower elevation angle? That is the typical example. What are the problems? If the elevation angle is low, I said below 15 it is not recommended. Why?
Ground noise.
Ground noise. One is lot of ground noise will be picked up by the side lobe. And other is rain attenuation will be over longer distances now, therefore heavier attenuation will be recorded. And the amount of noise, atmospheric noise getting added will be much higher. So those are the main reasons. We will make a list of the reasons because it's a typical question in the paper. You can write. We will write it as an answer directly. Low elevation angle of the beam with respect to Earth's surface leads to the following problem. Number 1, the main beam goes over a long path distance. Therefore, higher delay and more free space loss. Number 2, side loads and part of the main beam pick up scatter noise. Scatter, S-C-A-T-T-E-R. Scatter noise from Earth. They also pick up thermal noise from Earth. Scatter noise means reflection. Okay? They also pick up thermal noise from Earth. So underline scatter noise, underline thermal noise. Two different things. Scatter means reflection. Thermal means the heat. Number 3, sky noise temperature increases. sky noise temperature will be high. Sky noise temperature will be high. Number 4, figure of merit. Figure of merit capital M will be low. Therefore, poor EB over N naught ratio. Poor EB over N naught ratio leading to high bit error. Next one, higher rain loss. Higher rain loss. Come on, cloud loss. Cloud loss means you are going through the cloud. Cloud loss and atmospheric absorption loss. Higher rain loss, cloud loss and atmospheric absorption loss. Due to the slant beam, slant, SLANT, slant beam. Due to the slant beam. Okay, so those are all the problems that will come if you operate at low angle. On the new line measure, below 5 degrees, new line below 5 degrees, do not operate. Below 5 degrees, do not operate. You can't get the signal. 5 to 15 degrees, next one 5 degrees to 15 degrees, not recommended. Not recommended because when it rains there will be no signal. Not recommended. 50 to 90 degrees, possible to operate. But higher the better. Higher is better. That means higher angle is always better. So these are the general ideas from experience. Right? Okay. So that's all about the SATCOM. And you can look at the SATCOM note in the diploma also. There will be some more details like beam isolation and things like that.
So azimuth angle here?
Azimuth means elevation means you are elevating the antenna from the ground. Azimuth means supposing this is the Earth station, but the satellite is there, and supposing this is the north of the Earth station. Assume this is the north. From the north towards the satellite you have to rotate, and then only you have to elevate. Okay? This rotation angle is called azimuth. Shall we write that also if it is a question on the paper? New line you can write. The azimuth angle is the angle by which the earth station antenna should be rotated. In the horizontal plane. Be rotated in the horizontal plane from the north of the station. Until the line switch. The subsatellite point. New line elevation angle. The angle by which the beam should be elevated from the horizontal plane, at the station until it aligns with the satellite. So is it clear? If you have the notes here, then in the azimuth plane you go theta azimuth, then from here you go elevation. So first azimuth, then elevation, then you will be seeing the satellite. That's the normal procedure. Okay? Basically we have covered all, I think. So from next time we can start revision. And when you come, have your answers ready for all past tests. Right? You have to do within 1 week all past tests. So maybe you should apply leave, I don't know. Right? But I want you to have a ready-made answer set in which you have answered the questions you can answer, but certain parts can remain unanswered if you find them difficult. So bring it with the question paper, because we will not be discussing whole question. We will be discussing only the difficult point. So if you don't have the full answer with you, at least the other part you won't understand. So the revision will be very frustrating if you come like that, unprepared. At least prepare like that, have the answer sheet ready, then you can quickly rotate, see what you have done, and if you find any doubtful place or difficult place, I will explain there, then you can correct it. And while you are answering at home, please time your answers and write down the timing. Then if there is a timing problem, you will know before you go to the exam. And there is still time to correct, I think. So please identify within this space.